What's up, everyone? This is LeetCode 46, Permutations. So we've done combination sum previously in the grind 75 list. Now this is different, obviously, but right, just make sure you understand the difference between combinations and permutations. So here, for example, we just have to return basically an array of arrays of all the different possible rearrangements of all the elements of an array. So right, so if we have 1, 2, 3, right, we can have, right, we have to return that as well as 1, 3, 2, 2, 1, 3, 2, 3, 1, etc., etc. I don't think the problem statement and understanding what your goal is with this problem, that's not really that tricky about this problem. Like, even on the surface, right, like, you can kind of understand what we have to do, right? We just have to basically return all the rearrangements of the input array, right? The possible rearrangements of all the elements in the array. So how are we going to do this, right? So I'm going to kind of show you an illustration, and after that, we're going to start working a solution, and I'll show you 3 solutions from least optimal to most optimal, and we'll just go ahead that way, okay? The reason I show you 3 is because the least optimal one, I think, shows you how to do the problem and kind of what we're doing, but we can optimize it and make it better, okay? So we'll get down here a little bit later, okay? So we have our input, right? Our array, which are integers, right? That's our input. And so we can have like a decision tree, right? And so, for example, initially we have to build out a certain permutation, right? So we have our empty array initially, right? And we can take 1, 2, or 3, right? Right. So that's why our decision tree branches off, right? Well, when we take 1, we have 2 and 3 left over to pick from, right? So we can branch off to the 2 or the 3. And obviously, when we go down this path of 1 and 2, we can only pick a 3. So this would be one permutation. This would be another one. And then same with the 2s, right? When we branch off to a 2, right, we can only take a 1 or a 3, right? If we take a 1, then we can take a 3. If we take a 3, then we can take a 1. This is, right, one permutation. And this is another permutation. I think you understand, right? So this is conceptually like this. It's not exactly like well, it's a little similar to the combination sum in the sense like you have to make certain decisions when you're at a certain point, right? Because obviously you can't reuse numbers, right? So how are we going to solve this? And really, the easiest way I can explain this and how we're going to approach this is, right, we have this input, right? And what we're basically going to do is we're going to have a for loop, right? And within that for loop is where we're going to do like recursion calls, okay? So what I mean is we're going to go in a for loop, right? And we're going to, so from left to right, right? Like a normal for loop. So we're going to pick a 1, right? And that's our array so far. Then in the for loop, we're going to go in again and we're going to say, okay. Or we're going to recurse, right? So we're going to go do a recursion call and we're going to do that for loop thing again. So we're going to go, okay, 1. Did we pick 1 yet? Yeah, we already picked 1. Okay, so we can't go 1. What about 2? No, we didn't pick 2, so we can pick 2. And then we can do a recursive call again, right? And so we can go again. So let's do, okay, 1. We already have a 1. What about 2? Okay, we have a 2, but not a 3. Okay, so now the permutation array so far is equal to the length of the input array. So what we do now is we take this, right, and we put it as an array into the output array. Okay. Now, what do we do after this step though? What we're going to do is we're going to pop from here, right? We're going to pop from here. And remember, in the previous recursive call stack, when we added, so on this third recursive call stack, we added the 3. But when we pop out, we go up the call stack, right? When we added the 2, initially, right? Well, that's a for loop as well, right? So we would pop, when we go up the recursive call stack back to 2, we would pop the 2, move on to the 3. So we add a 3 here, and then we recurse into the for loop again, and we go, okay, is 1 in it? Yes. 2 in it? No. Right? And so you can see how we're building our permutation. So when we go all the way back up to the first for loop, right? That specific call stack, we're gonna go into the 2, right? And now we're gonna, so we picked a 2. Now we're gonna go in the for loop again because we're doing a recursive call stack. So in the next for loop, in that recursive call stack, we're gonna okay, is 1 in there? No. Is 2, and then we do that, right? And then we do a recursive call for that. And so we kind of build out all our permutations basically by doing it like that. I hope that makes sense. It's really easy to understand once you see the code, but yeah, I'm not gonna do this. This is just what I was showing you up here. So the way we're going to do this is, first of all, let's just define really quickly a function for backtracking, right? Let's make our answer array because this is what we have to return. And in this answer array, we're going to have a bunch of lists, right, of the different permutations. So we're going to have to return this down here, and we're going to call backtrack. Okay, so now this is where the bulk of our work happens, right? So first of all, we're going to say, and we actually need a permutation array also. So we're going to create that. Now up here, right, by the way, I guess we can do this. There also is an edge case. Like if you look at the constraints, nums.length can be at minimum 1. So if that's the case, we can just return that element, right? Because if there's only one element, obviously, it's just a list of that. So we have to do it like this. We're gonna have to do return nums.copy. Okay. The reason we have to do it this way though, when we return, because you can't do like, you can't return like nums of 0, because what this would do is it would put a number in the output array, but you can't have a number. It has to be an array of arrays basically, right? So you have to do it like this. So you basically copy the array and put it into the answer array. Well, we're not using answer, but you basically create an array of array by doing this. Okay. So that's just like an edge case that we have to handle, like, because we can have a constraint of minimum of 1, right? So we have our answer array and our permutation array. We build up our permutation array until it's equal to the length of nums, and when it is, we basically put the permutation array into the answer array. Okay. So the way we're going to do this is we're basically going to have a base case, which is going to say if the length of the permutation array is equal to length of nums. And actually, let me copy this and reload my page because the color coding is not working. Oh, there you go. LeetCode is really slow sometimes. So if the permutation array, we build it up and it's equal to the length of nums, we know that we can just append it to answer, right? So we're going to say answer.append permutation array, and we have to make a copy. And again, if you watch my combination sum video, we have to make a copy because in Python, if we just add perm array, it would be a reference to the object, not an actual copy. So we want to actually copy the elements. So we do like that, we return, right? Okay, now down here's where our recursive call stack goes. And again, this code's going to be not that hard to understand, right? So we're going to say, we're going to do this, okay? So we're going to iterate through this array, and we're going to basically, when we go through a number, if that number is not in the permutation array, we can add it and then do the recursive call, okay? So we're going to say perm array dot append x, right? And out here is where we pop, right? So when we have when we're building up something like 1, 2, 3, this is our permutation array, by the way, not our input. So when we pop this, right? Well, there's no, for the for loop, there's no more to go to. So we go back and we pop this. However, on the call stack here, when we added the 2, there still is, we haven't gone through the full for loop, right? So there's a 3 left. So when we pop this, we can actually add the 3, and then we go recursive call again, and we do the for loop. Okay, 1 is in the permutation array, but 2 is not, so we can add it. And so that's how we get our different permutations, kind of like that, right? So it's not too difficult, but again, I think you need to, for me at least, specifically on this problem, make sure you actually write out your, walk through your code line by line and understand how we're handling the actual call stacks, the recursive call stacks, because it'll make more sense. Because trying to visualize in your head is a little bit difficult. And I believe that should be it. So this code is not too difficult, but it's slightly inefficient, and we'll talk about that. So the issue with this code is, well, first of all, for our permutations, we have n factorial, right? So whatever the length of this nums is, let's call it n, there's going to be n factorial permutations, right? That's just how many permutations there are. So if there's 3 numbers, we're going to have 3 factorial permutations, right? If the length of nums is 7, we're going to have 7 factorial permutations, etc. So the time complexity is going to be n factorial, but then we have this operation here where we have to basically check if something's in an array. In the worst case scenario, that's O of n. So our time complexity is O of n times n factorial, right? So we can actually simplify this a little bit. And what we can do is we can actually just use a set, right? So let's do this. So the reason a set would be more efficient, right, is because obviously the lookup on a set is O of 1. So what we can actually do is change this algorithm to basically go from time complexity wise from O of n times n factorial to O of n factorial. Okay. Now the issue is we're using a little bit more space, right? And so that's why this is the second solution, slightly less optimal. And then third, there is a third solution which I'll show you, which is O of n factorial. But the time complexity or the space complexity is not like this. So this uses a little bit of space. And so this is why this is still better than the first solution I showed you, but it will be more optimal, right? So let's use an array, and really the array, or not the array, sorry, the set. The set is just for this, right? Just don't over confuse yourself. This second solution is using a set only to help us with the lookup, right? So what we're going to do is we're going to say for x in nums, nice, and we're going to say if x not in used, right? Because used is our set, right? We're going to add that number to our set. We're going to append that number to our permutation. We're going to pass this the permutation array. So we don't need to pass it the permutation array. And then out here, when we pop the permutation, the element from the permutation array, we need to make sure we remove it from the set as well, right? So we have something like this, right? Or actually, we do need this permutation array. Sorry, because in here we can just pass in an empty list, right? Because remember how we were using an actual array up here? We can just pass an empty list and use that as the, rather than holding an array up here and creating it and all that, we can just pass it an empty list and use that as our permutation array. But again, this second solution is a little bit better, but it does use a little bit of space, and because we have the set, and on top of that, right, there's a solution, right? So now we have an O of n factorial time complexity solution, but we can have another solution which is O of n factorial time complexity, but the space is less, right? So the way to do that is basically the way we're gonna approach this is by swapping the elements. Okay, so I'll show you how we're gonna do that. And by the way, I will show you in an illustration so you understand how the call stack works, because this third solution is simple to understand, but like visually I had trouble like understanding like what we're doing, right? So we're gonna create a function called backtrack, and we're gonna have a starting index, right? And we need to call that down here, pass it the 0th index, and we have to return the answer. Okay, now up here is where the bulk of the work happens, right? So we're gonna have a starting index, right? Initially is at the 0th index. If that reaches the end of the array, the input array, then we can just append copy, right? You see how we're not using any extra space right here, right? And then down here we have to do basically the same thing with the for loop, but slightly different. So we're really using basically two, you can think of it kind of like 2 pointers basically. It's not exactly a 2-pointer problem. It's not that simple because we have a call stack, but I will show the call stack, right? Because we're not using 2 pointers, because again our for loop starts at the index and goes all the way forward, right? So we're basically going to get to the end of the array, and then we're going to backtrack and do some swapping and stuff, which is useful. Or I think we we do the swapping first, excuse me, and then we basically keep iterating all the way to the end of the array. And then on the backtrack, well, when we hit the end of the array, that's when we add stuff to our answer output and our append to our answer. And then on the way back, we kind of unswap stuff, right? So, and again, I will show you an illustration here after we finish writing this, right? So we have an index, a starting index, and we have nums of I. And on Python, you can do the swapping on the same line, unlike something like C++, where you'd have to have like a temp variable or something. So this is kind of the neat part about Python. And then here we have to do the recursive call, right? So we're going to say bt start index +1. Okay. And then down here, we're going to say nums start index. We can just copy this. Because down here, all we're doing after we exit the recursive call is we have to swap the elements back to the original place. Why do we have to do that? Because we're in a for loop, right? So when we go to the next I, we want to make sure we don't have our elements jumbled up, right? We want to have them in the same place, basically. Okay, so this is kind of like a cleaner, neater, simpler solution. I'm gonna say for I in, a neater, cleaner, simple solution where we're not using extra space, right? You see, we're not using a set or anything, and it's still O of n factorial, and complexity, right? So this is kind of the most optimal solution, but I want to show you that first solution because just so you kind of understand how you can get permutations. Because I think this is a little bit cleaner, but it's hard to visualize in your head even more so. So we're gonna go through how this swapping happens, okay? So I drew this out, right, and kind of step by step. It's not perfect, right? I'm not claiming it's perfect, but I think it'll get the point across, right? So again, when we start, we have our starting index, and that's passed in as 0. Okay, so we start at the 0th index. Okay, and then we have enter this for loop where we start at the 0th. We start at I at 0, but the 0 is the same place that the starting index is. Okay, so you kind of understand. They kind of the quote unquote pointers, right? The starting index and the I, they start at the same point. Okay, so if I is 0, right, I is going to start at 0, starting index is going to start at 0, etc. And if we recursive call and this start index goes up to 1, the I is going to start at the 1, right? Because the starting position is whatever start index is up to but not including the length of nums, right? So when we start off, we're going to have something like this, okay? So the starting index and the I are going to be here, right? Then we're gonna right, they're gonna be there. We're gonna swap, but technically they get swapped at the same place, so it's the same, right? And then we move forward to start index +1, and we do the same thing. Technically, you can't swap these. You can, I guess, but I mean, well, they're the same. They're the same thing, right? You're swapping the first index with the index, if you get what I mean. Then we go to the second index, right, and do the same. Okay, now when we move forward, start index +1 again, we're out of bounds, right? So when we're out of bounds, what we're going to do is we're going to append this, right? So technically 1, 2, 3 gets appended to our 1, 2, 3 gets appended to our answer array. Okay, and I will print this actually, just so you kind of understand what are we adding at every step, right? So what happens now is we basically, so we hit this return statement down here, right? So we basically exit this and we have to swap the elements back. Now 3 and 3, you can't swap that. I mean, there's no need. I mean, technically we're checking the swapping. We're doing the swapping operation, but you're swapping an index that's at the same index that you're comparing it with. And then you basically go back because there's nothing left in the for loop, right? So you go back. And now we're at this 2, right? Now we're at this 2. So kind of like that second example where the I keeps going, right? The same thing happens here. So even though S index is here, the I needs to move forward, right? Because we're not done with our for loop for that call stack that we just went back to. So now 2 is here and I is here. So now that we do that, we're in the for loop again. So remember, in the for loop, we have to do the swapping and then the recursive stuff again, right? So now this has to get swapped. So this 2 and this 3 get swapped, and we have 1, 3, 2, right? And then again, when we move S index forward, after we swap the 3 and the 2, we move S index forward, right, by 1. And so we have to do basically swap and recurse the 2 with itself. So again, nothing would happen. And then we move S index forward. It's out of bounds, and so we add 1, 3, 2 to our output array. Okay. Now we're out of bounds, right? So we need to basically go back up the call stack and swap the elements back. Of course, this 2 swap with itself is going to stay there, right? Go back up the call stack, and basically this 2 and this 3 get swapped back. And so now we're back where we were, right? So when we were up here, right, we handled we're at the 2, right? And again, the reason this is hard to explain is because technically we're in a recursive call stack where we first are in the recursive call stack with 1, where we just swap it with itself. 2, where we swap it with itself. 3, where we swap it with itself. So it's a little hard to explain. But the reason we need to do that is because we need to add the original input array as a possible permutation, right? Like 1, 2, 3 is a permutation of that input array, right? So we swap these 2 back, right? So we swap the elements, and we keep iterating through the for loop. We can't, so we go back up the call stack again, right? And so when S index is here, right? Or sorry. What happened is initially our call stack was 1, 1, right? So we handled all the permutations before, and remember when we do all these specifically. So we went into a call stack here so that we can basically swap the 2 and the 3 and stuff, and also basically add the permutation 1, 2, 3 to the whole thing. But now we're in the first for loop, right? The call stack there, and we're still in the for loop, right? So we handled the starting index is at 0, but we handled the case where it was 0 recursively, and so now we move forward in the I once. So now this goes here, and again we have to swap that, so we get 2, 1, 3. And we move the S index forward by 1, and we do the same thing, right? We add this, we go here, right? We do the same thing. We move I index forward once, and we get 2, 1, 3. We add that to our output array, right? 2, 1, 3. And now when we back up, right? When we back up and we get to this call stack here, whatever this call stack is, right? I has to move forward, so we have to swap this and do 2, 3, 1, okay? And I hope you get the point. And so that's kind of how because I don't want to keep drawing this out. It would take a while, but, or maybe not that long, but I hope you kind of understand how we're moving forward as far as this answer goes, right? Like we're basically going for, we're going forward all the way until the end. And then once we're out of bounds for our permutation, using like kind of the pointer, right, with the starting index, that's basically when we add that entire thing to the answer array, and we basically backtrack, okay? And we keep doing different combinations, keep backtracking, and then when we get all the way back to where we started, we basically have the starting index here, but the I moves forward, and so then we do the swapping there. So we have 2, 1, 3, and then we need to keep going all the way, and our way back we're going to keep getting our permutations. So basically you are permutating the first time around by having the I move around and stuff, but you basically keep going all the way till the end, and on your way back is where you get the different permutations with let's say the first, the 0th index starting with a specific number like 1 or 2. So you want to build out all those permutations, right? Obviously, that makes sense, right? We have a 1, a 1, a 2, a 2, a 2. But then on our way back, right, we want to make sure we get the permutations of this before we move on to the 2, right? So when we're here, we get this, but on our way back, we want to make sure we get the permutations of this before we move on from this 2, right? So I hope that makes sense. I know this video is a little bit long, but I just want to explain all these things just so you kind of understand what we're doing. Okay? Anyways, I hope this helped, and I'll see you next one. Peace out.